Another kind of function that we can occasionally get values for limits at infinity for are algebraic functions. Algebraic functions are basically a lot like rational functions, where they're built mostly out of ratios of polynomials, except you can also have roots of any order, so square roots, cubed roots, fourth roots, and so on. So this, for example, this function here, if you ignore the square root, it looks like it's a rational function, but the square root makes it algebraic instead of rational. Okay, so what can we do to find a limit as x goes to infinity for this function? Well, if you just try to plug in infinity, quote unquote, in the numerator you get infinity, in the denominator you get infinity. So again, infinity over infinity, that doesn't tell us anything about what the limit of this might be. So we have to try something else. Now the thing about algebraic functions is, if you want to know a limit at infinity, right, since they're so much like rational functions, why don't we use the same trick as we did for rational functions? So multiply the numerator and denominator by some power of x. All we need to do is choose an appropriate power of x to use here. Well, when we were dealing with rational functions, what we looked at was the degree of the numerator and denominator, but algebraic functions don't really have a degree, but they kind of do. So the numerator is a polynomial, so its degree is definitely 1. What about the denominator? Well, there's an x squared here, but it's inside of a square root, right? A square root is like a power of a half, and so if this x squared on its own counted as degree 2, since it's being raised to a half, it really counts as degree 2 times a half, so that's degree 1. So it's as if the numerator and denominator are both degree 1, even though the denominator doesn't really have a degree. But if the numerator and denominator both kind of have degree 1, then we should use x to the first power here. All right, so that's the idea anyway. Now let's see if the idea does us any good. So let's distribute this 1 over x through the numerator and denominator. So limit as x goes to infinity of, distributing through the numerator, we get x over x is 1 minus 7 over x. Now in the denominator, things are a bit more complicated. So when we distribute our 1 over x through the denominator, we get 1 over x times the square root of 3x squared plus 5 minus 2 over x. And at this point, we can't yet tell what value this might produce in the limit, because, right, we know that this 7 over x term, since x is going to infinity, 7 over x is going to go to 0. Same for this 2 over x term. But if we look at this term here, 1 over x is going to 0. The stuff in the square root is going to infinity. And what does 0 over infinity mean? Well, we can't tell which one wins, right? 0 is trying to make this product small. Infinity is trying to make this product big. And we can't tell which one wins. So we haven't done enough to figure out what the limit is yet. We need to sort of work on the algebra of this a little bit more. One thing you might think to do is, well, let's combine the 1 over x with the stuff inside the square root. We can do that, but first we have to arrange for this 1 over x term to have a square root of its own. And that is possible. To do that, right, 1 over x is the same thing as 1 over the square root of x squared. Now this isn't always true. This is only true because x is going to plus infinity. As we'll see in a moment, if x is going to negative infinity, this is actually different. Right? But if x is positive, then x is equal to the square root of x squared. And x is positive since we're going to positive infinity. All right, so times square root of 3x squared plus 5 minus 2 over x. Now we can put these square roots together. So limit as x goes to infinity of 1 minus 7 over x over, now inside this square root we have 1 over x squared times 3x squared plus 5 then minus 2 over x. So limit as x goes to infinity of 1 minus 7 over x over square root of, now when we distribute this 1 over x squared inside of this square root, we get 3 plus 5 over x squared. All right, and minus 2 over x. Now, because we don't have any x, because the only places we have x are in the denominators of these little fractions, now things are looking good for just plugging in infinity, or taking the limit immediately. So 7 over x, as x goes to infinity, that goes to 0. 5 over x squared, that's going to 0. 2 over x, that's going to 0. And so our final result is 1 plus 0 over square root of 3 minus 0. So 1 over square root of 3. So the value of this limit is 1 over the square root of 3, which is a bit unexpected, but right, we're still using the same algebra trick that we did with rational functions, but there's just this added wrinkle of having to get our 1 over x inside of the square root by doing this algebra trick. All right, well, let's see how this works out if we take the limit at minus infinity instead. You can bet we're going to have to do the same algebra trick, so let's just do that right now. We get the limit as x goes to minus infinity of 1 minus 7 over x over 1 over x times the square root, 3x squared plus 5 minus 2 over x. All right, now this is where we made the square root show up right here. So let's do that. Limit as x goes to minus infinity, 1 minus 7 over x over, so there's going to be a square root of 3x squared plus 5, and over here there's going to be a minus 2 over x. But we need to figure out what do we do with this 1 over x? So the temptation is to say, well, 1 over x is equal to the square root, 1 over the square root of x squared. But that's not true. And the reason is because if x is negative, right, we're taking a limit as x is going to minus infinity, so x is negative. Well, if x is negative, x is not equal to the square root of its square, right? Because the square root of its square is going to be positive, but we said x was negative, so these two can't be equal. In fact, if x is less than or equal to 0, x is equal to the negative of the square root of its square. So what we need to do is put an extra minus sign in here, right there. And that's going to change the final result that we get. So if we continue with our calculation, we get the limit as x goes to minus infinity of 1 minus 7 over x over, now this minus 1 stays outside the square root, right? We're just moving the 1 over x squared inside the square root. So square root of 1 over x squared times 3x squared plus 5 minus 2 over x. And now when we distribute through here, we get limit as x goes to minus infinity of 1 minus 7 over x over minus the square root of 3 plus 5 over x squared, and then in the denominator outside the square root, minus 2 over x. And now we can take the limit as x goes to infinity. 7 over x is going to 0, 5 over x squared is going to 0, 2 over x is going to 0. And so we're left with 1 over the negative square root of 3. So negative 1 over root 3. So you can see the limit at minus infinity is actually the negative of the limit at plus infinity. So we do have to be careful to keep track of whether we're taking a limit at plus or minus infinity. If you ever have to use this square root trick, it matters whether you're taking a limit at plus infinity or at minus infinity. All right, so for one final example, let's look at this one, the limit as x goes to plus infinity of the square root of 9x squared minus 4, and then outside the square root, minus 3x. So if we try to plug in infinity what we get here is infinity minus infinity, which isn't very informative, because infinity minus infinity, depending on how these infinities come up, the infinity minus infinity might give us infinity, or some number, or 0, or maybe a negative number, or maybe minus infinity. It really depends on how these infinities came about. So this is just another way of saying that we need to try harder. So let's try some algebra trick. What should we do? Well, it's really kind of hard to say. It's not at all intuitive. But there are only so many tricks that we have. And because there's no denominator, it doesn't really seem clear if or how to use this 1 over x trick like we were using before. Another thing that we could try to do is, when we have, in situations where we have a square root, one algebra trick we've used before is this conjugate trick. So if we write this as square root 9x squared minus 4 minus 3x over 1, we could use our conjugate trick and multiply the numerator and denominator by the square root of 9x squared minus 4, and then instead of minus 3, plus 3x. And then do that in the denominator as well. Square root 9x squared minus 4 plus 3x. Okay, so, it's hard to know ahead of time if this is going to be helpful, but it's definitely something we can try. So if we multiply this out in the numerator, we get limit as x goes to infinity. So in the numerator we get 9x squared minus 4, and then the cross terms cancel, and minus 9x squared. And then in the denominator, square root 9x squared minus 4 plus 3x. Okay, well now you can see some things in the numerator cancel. We get the limit as x goes to infinity of minus 4 over square root 9x squared minus 4 plus 3x. Alright, now this seems sort of like a good point to pause and take stock, because we introduced some complication, but then a lot of it simplified away. So let's pause and take stock. What we could do is see if the situation with infinity minus infinity has improved at all. In other words, try just plugging in infinity again. And again, I'm putting air quotes around plug in infinity. We aren't actually plugging in infinity, but we're just seeing what the trend of these x's does as x gets really big. So numerator is minus 4, so it just stays minus 4. Now this stuff inside the square root, it's a quadratic that's opening up because it's positive 9 here. So the stuff inside the square root is a big positive, and getting bigger, plus, well, this 3x, x is going to plus infinity, so 3 times x is getting really big. So what happens to this whole thing? Well, minus 4 over this denominator, there's no ambiguity now, right? The problem at the very beginning of this example was we had infinity minus infinity, but this time we have infinity plus infinity, so there's no ambiguity about that. That's really big. And minus 4 over something big and getting bigger, that's going to 0. So this limit is actually 0. So I know I said at the beginning that infinity minus infinity isn't always 0, and that's true, but this particular example does turn out to be 0.